Hello again. This is our next video lecture, and it covers Chapter 5, Section 3 in Fundamentals of Physics. That section is entitled Applying Newton's Laws. And of course, that name is appropriate because that section, if you read it in the book, has lots of example problems. But there's also one new key idea introduced that we're going to talk about first. It's called Newton's third law of motion. As you will remember, in this chapter, we are studying the field of dynamics, which is explaining why a particle moves the way it does, the cause of its motion. And to do that, we have introduced, so far, Newton's first law of motion and Newton's second law of motion. Here comes the third. But let me try to give you some context here before we get into the details. Of the three laws of motion ascribed to Newton, by far the most important is the second law. That law, at the end of the day, is what tells us why a particle moves the way we observe it to move. Specifically, the second law tells us how to find the acceleration of a particle. The second law tells us that the acceleration vector equals the net force vector divided by the mass. And so, if we want to understand why a particular particle accelerates the way it does, we define that particle to be what we call a system. We draw a complete free body diagram for that system, and then apply Newton's second law to that system. It turns out Newton's first law and the third law are just helpful tools in applying the second law. And that's the way I recommend you think about this. The third law is going to be helpful, but it's just a tool for the most important law, which is the second law. I'll also give you a heads up that the third law of motion is one of those trite laws of motion in the sense that there is a kind of common way of expressing the third law of motion that is trite, simple to say, and many people can say it, but there's not necessarily a deep understanding of what that means. Okay? The trite version of Newton's third law of motion, which I suspect you all have heard, is, for every action, there is an equal and opposite reaction. Heads up, if I ever ask you to state Newton's third law, do not say what I just said. I don't like it because it's trite and commonly used in society without understanding. Here's the way we're going to state Newton's third law of motion. Okay? So here we are. Key idea, Newton's third law of motion. We're always going to be talking about two particles when we are talking about Newton's third law. Two particles, two things. I'll label them for now A and B. Particle A and particle B. Suppose particle A and particle B interact with each other. Somehow. Right now I don't care how, but they interact with each other. What that is code for is that they exert forces on each other. Here's what the third law says. The force on A due to B, force on particle A due to particle B, and the force on B due to A, the force on particle B due to particle A, have equal magnitudes but opposite directions. The force on A due to B and the force on B due to A have equal magnitudes but opposite directions. That's how we're going to state the third law. It says in very succinct physics words what we mean. Okay, let me start with some pictures then to think about this. Here I've drawn a little schematic of a surface of some kind, and sitting on that surface are two particles. A is, let's say, a marble, and B is a cube of some kind. And I have put them right up against each other so that they are in contact. They are touching. some of their atoms are coming together. We'll call that an interaction. So that there's going to be a force on one due to the other. There'll be a force on the marble, A, due to its contact with the cube, B, and there'll be a force on the cube, B, due to its contact with the marble, A. So, what I'm going to draw now are free body diagrams for each particle, the marble A and the cube B. When we draw free body diagrams, we represent the particles as dots. So that's what you see now on the right. A and B are just represented as dots. And when I draw the free body diagram for A, I draw only the forces acting on A. And all the forces acting on A. So let's look at that. I'll highlight these forces on A as I talk about them. There are, in fact, a grand total of 3 forces on A. There is a vertically downward force due to gravity, F-grav on A. I just highlighted that green arrow right there. There is a vertically upward force on A due to the surface it's sitting on. I just highlighted that one. We would call that the normal force, right, from a surface, and it's perpendicular to the surface. Okay, and so there's that one. And then there's the contact force on A due to B. Our intuition tells us that if A is on the left and B is on the right and they're up against each other, that the force on A due to its contact with B will be to the left. I just highlighted that force arrow. And that's going to be labeled here. Now I'm going to delete that little drawing I just did so that we can see. That force is going to be labeled F sub AB. That notation is important. That notation means the force on A due to B, from B. That's the complete free body diagram for the marble, particle A. Now let's draw a separate complete free body diagram for particle B, the cube. Again, there's a grand total of 3 forces on the cube. For example, there's a downward gravitational force, F grav B, which I just highlighted. Notice the length of the F grav for B is longer than the length of the F grav for A. What is that telling you? It's telling you that B has more mass than A. Because remember the formula for calculating the magnitude of F grav? Take the mass of the object times little g, the gravitational field strength. So a longer F grav arrow for B compared to A means B must have more mass. There's also a normal force on B, vertically upward. There I just highlighted that, labeled it FNB, the normal force on B. And then there's a force on B due to its contact with A. Force on B due to A. And now I'm going to draw that one. It's right there. And I'll circle the label for it. Right there. Force on B due to A. And what Newton's third law tells us is how to compare that force on A due to B, and that force on B due to A. Notice the forces are on different things. There's one force on A, and there's one force on B. And the third law is telling me information so that I can compare those two. And what the third law is telling me is that the magnitude of the force on A due to B, notice that notation means magnitude, is equal to the magnitude of the force on B due to A. Force on A due to B and force on B due to A. Equal magnitudes, but opposite directions, as the free body diagrams there show. Okay? So that is useful. This new law, the third law, it can be useful when you're applying the second law. It is just a tool in using the second law. But let's make sure we understand this tool. Here's one thing to note. The third law is always referring to 2 particles. Please note the pattern. When you're invoking the third law of motion. Two particles, if I call them A and B, then we're saying force on A due to B and force on B due to A. Force on A due to B and force on B due to A. We're always talking about two particles. This law, based on experiment, has always been found to be true regardless of the relative sizes or masses of the two particles. This one, people struggle sometimes to accept this part of it. Let me show you a little more what I mean, or talk about what I mean. Now what I have are just a couple of photographs. And on the left here I have a photograph of, this happens to be identical twin tennis players who, in this whimsical photograph, have jumped off the ground and are bumping off each other, and the photograph was taken while they're in contact. Okay? So if we call the twin on the left twin A, probably can't see that, and the twin on the right twin B, then when they're in contact with each other, they exert a force on each other. The force on A due to B would be to the left. The force on B due to A would be to the right. And those forces have equal magnitude. Third law. I think most people are willing to accept that for something like identical twins, which presumably have nearly identical masses. But now look at the next photograph, the one on the right. It shows a tugboat, the small boat, in contact with a big tanker ship, the big one. And let's call the tanker particle A and the tugboat particle B. They're in contact, so they each exerts a force on the other. The force on the tanker A due to B is going to be roughly to our left. And the force on the tug B due to the tanker A is going to be roughly to our right. And the third law says that those forces have equal magnitudes. Doesn't matter that one has a lot more mass than the other. If they are in contact, and so that there are forces between them, the force on the tug from the tanker and the force on the tanker from the tug have equal magnitudes. We must accept that, because that's what the third law of motion says, and it's been tested by experiment. Now, I think what causes people trouble in accepting what I just said about the tanker and the tug, and the fact that they exert equal sizes of forces on each other, is because they're confusing an application of the third law with the second law. If you want to know why the tanker ship is accelerating in a particular direction in this scenario, you need to look at all the forces on the tanker, all of them. Only one of those is from the tug. So the force on the tanker from the tug, that force alone is not enough to understand why the tanker is moving the way it is. To understand why the tanker is moving the way it is, you must get the net force on the tanker. And one of those multiple forces on the tanker is from the tug. Similarly, if you want to understand why the tugboat is moving the way it is, why it has the acceleration it does, you need to add up all the forces on the tug. Only one of those is from the tanker. Okay? So again, if you want to know why a thing is accelerating the way it is, you need to know the total force on it. Okay? So we have our big tanker and our little tugboat, and yes, they exert forces on each other, and the magnitudes of those forces are equal. But that's not the total story as to why each one moves the way it does. Let's continue practicing applying the third law to the drawing at the bottom of this slide. It shows a swimmer pushing off the wall to swim down the lane in the pool. Okay? And what we would observe here in watching the swimmer is that this swimmer has an acceleration to the left. And we'd like to understand why that's happening. Why does this swimmer have an observed acceleration to the left? To understand why a system, the swimmer in this case, accelerates in a given direction, you apply Newton's second law. So I need to know the net force on the swimmer. The swimmer. That means I need to know all the forces acting on the swimmer. No other forces are to be considered. Only forces on the swimmer. Now, the drawing here, it's my contention, is drawn intentionally to see if they can, well, I won't say they're trying to confuse you, but they're trying to force you to grapple with some of the subtleties of the third and second laws. Because they've drawn some force arrows. They've drawn two of them in this drawing, force arrows, and labeled them, two forces. But neither of those constitutes a complete free body diagram for anything. So if we want to understand why the swimmer is accelerating to the left, we will apply Newton's second law to the swimmer and account for all the forces acting on the swimmer. Now the drawing shows one of the forces on the swimmer over here at the point where the swimmer's foot touches the wall. That's where the force is acting. And the way I would label it, which is a little different than the way it is in the drawing, is that it is a force on the swimmer due to the wall. And it is to the left. All right, that's a force on the swimmer. That's going to be part of my application of Newton's second law to the swimmer. Are there other forces on the swimmer? Yep, there are. I mean, this is all happening on Earth. So there's a downward force due to gravity, F grav. I won't even bother drawing it. But there's also an upward force. We haven't talked about it, but you might know about it. When an object is immersed in a dense fluid like water, there's what's called a buoyant force. And in this case, the buoyant force on the swimmer is upward, and in fact balances the downward gravitational force. So I won't even worry about them. It's this force right here, this leftward force on the swimmer due to the wall, that explains why the swimmer has an acceleration to the left, over here, where I've drawn the arrow, just to represent the acceleration. That explains why the swimmer is observed to accelerate to the left, because there's a net force on the swimmer to the left. What's it come from? The wall. Stop. You're done analyzing the swimmer. You are to say nothing at all about that other force in the drawing if what you're analyzing is the motion of the swimmer. Okay? Now, the reason the people who made this drawing drew this second force arrow, which I will now talk about, the one pointing to the right there, is because they're wanting to talk about Newton's third law. Newton's third law is talking about two things, A and B. In this case, the things are swimmer and wall. Two separate things, swimmer and wall. And the third law says that if there is a force on the swimmer due to the wall to the left, the one I've just labeled, then there is a force on the wall due to the swimmer of equal magnitude and to the right. Okay? And that's that arrow. But these two green arrows that I now have in my drawing are on different things. One of those arrows is a force acting on the swimmer, it's to the left, and the other arrow represents a force acting on the wall, it's to the right. Now, if I wanted to understand why the wall does not move, right, presumably it does not move, I would need to apply Newton's second law to the wall. And if I observe the wall to have zero acceleration, then it must be true that the net force on the wall is zero. And so there must be other forces on the wall that aren't even drawn here to make the net force on the wall equal to zero. But let me emphasize one more time, you do not use this force right here that I just circled. You do not use that force at all to explain why the swimmer accelerates to the left. Yet these two force arrows here and here are what we call a Newton's third law pair. Force on A due to B, force on B due to A. Force on swimmer due to wall, force on wall due to swimmer. You can always tell when the third law is being used or discussed because of the pattern I just invoked. You'll have a force on A due to B and a force on B due to A. Then you know force on A due to B, force on B due to A, equal magnitudes, opposite directions. But again, at the end of the day, the third law is just a tool to help us apply the second law. So what I want to do now is an example problem, Wiley plus problem. That gives us an opportunity to practice applying the second law and using the third law along the way. Okay, so what I'm doing here is I took from Wiley plus the problem at the end of chapter 5. It's problem number 55. Okay, so in Halliday, Resnick, and Walker, our book, we're doing chapter 5, problem 55. Here's the wording of the problem. Two blocks are in contact. Well, you can see that in the drawing. On a frictionless table. A horizontal force, F, I'm going to call it, is applied to the larger block as shown in the figure below. There it is, right there. It's acting on the larger block, and it's pushing to the right. Now they're going to tell me the masses of the blocks. Block 1's mass, M1, is 2.3 kilograms, the bigger block. Block 2's mass, M2, is 1.2 kilograms, the smaller block. The magnitude of this applied force, magnitude, I know its direction is to the right, is 3.2 newtons. So that's what I'm given. Okay, here comes the first question. We are to find the magnitude of the acceleration of the two blocks. So first, ask yourself, which way are the blocks going to accelerate? They are going to accelerate, I contend, because there is a net force to the right. Remember, there's no friction with this between the blocks in this table. And if the net force is to the right, then Newton's second law tells me that there must be an acceleration to the right. And if I push on block 1 to the right, I'm going to effectively end up pushing block 2 as well, or it's going to end up going to the right. The whole kit and caboodle, as they say, consisting of the two blocks are going to accelerate to the right. A arrow. And they will have the same acceleration, yes? Because they're just being pushed together. Okay, so they have the same acceleration in this scenario. We are to find that magnitude of that acceleration. Okay, to find acceleration, it's Newton's second law. A equals F net over m as a vector equation. So now I want to talk about a systematic application of Newton's second law. How to do it, how to apply the second law systematically, carefully, in a way that will be very important if you're going to be successful solving these kinds of problems. All right, so I'm going to have to scroll up here a little bit so that I have some room to work. Okay. First, in solving part A, we're going to do a systematic application of Newton's second law. Let's note that the blocks have the same acceleration because they just move together to the right. Okay? And when we apply Newton's second law, really the first thing we have to do is decide on what we're going to call the system. The system is what we're going to apply Newton's second law to. And we, as the problem solvers, have to pick the system. A lot of the times that's not complicated because there's just one particle moving around, and so that's the system. But also, quite frequently, you have scenarios where there's 2 or 3 or more particles involved. Here I have 2 particles involved, yeah, 2 blocks. So now you have more options for what to pick as the system. You could pick block 1 only, if it's useful. You could pick the system to be block 2 only, if it's useful. Or you could pick the system to be the 2 blocks combined, if that's useful. But you got to figure out what you are going to pick for the system, state it overtly, so that the people know, everybody knows what you're doing, and then apply Newton's second law to that system. Since I want the acceleration of the 2 blocks together, it turns out that what I want to pick for the system is both blocks. Okay? Both blocks. I'm thinking of both blocks as one blob. Okay? One combined blob. Now, once I pick a system, you might call that step 1 in a systematic application of Newton's second law. Step 2 is draw, a complete free body diagram for the system that we just chose. And remember, a free body diagram for a system shows all forces acting on that system. And now I'm going to be even a little bit more specific. All external forces acting on that system. External means from the outside of the system. Don't ever include what are called internal forces for the system. That'd be a force that one part of the system exerts on another part of the system. Okay? Only forces from the outside. Remember, my system is both blocks together. So if one block is pushing on the other block, that's an internal force and would not be included in a complete free body diagram. Newton's second law tells us that only external forces can accelerate a system. So I will draw the complete free body diagram. I'll draw it over here to the side. That line there just represents the frictionless surface. When you draw the free body diagram, it's often useful just to represent the system as a particle, a dot. And now we draw the forces. When we do these kinds of example problems in class together, I'm going to ask you to give me, one by one, the forces that are acting. We're going to construct the free body diagram together, in other words. You can do that here if you want by pausing the video. Right? I think it would be good practice for you if you pause the video and try for yourself to draw the free body diagram for this system. Draw all the forces and label them that are acting on this system. Okay, did you try it for yourself? Let's do it now together. The obvious, easy one to start with is the force due to gravity. There is a downward force due to gravity. I'm just going to label it Fg. G for grav. The total gravitational force on both blocks. Note the magnitude of that would just be m1g plus m2g. Then it's on a surface, so there must be a normal force perpendicular to the surface. Like so. And I will just label that Fn. N for normal, perpendicular to the surface. And I can tell you something right away. Those two forces have equal magnitudes. And in fact, opposite directions. Don't they? How do I know that? Because there's no vertical acceleration for these blocks, right? There's no up and down acceleration this way. Okay? If the vertical acceleration is 0, the net vertical force must be 0. These are the only two vertical forces, the normal force and the force due to gravity. One up and one down. They must balance. Now here's an interesting question then. These two forces that I've just drawn have equal magnitudes and opposite directions. Is the reason that they have equal magnitudes and opposite directions because of Newton's third law. Equal magnitudes, opposite directions. Doesn't that sound like the third law? This has nothing to do with the third law. Nothing at all. How can I be so sure of that? Because these are both forces on one thing. This system of blocks. And the third law is always about two separate things. Force on A due to B, force on B due to A. These are both forces on the same thing, the force on A. Okay? And the reason they balance is because of Newton's first law. There is no y vertical acceleration, so the net vertical force must equal 0. Now, that's not the complete free body diagram. There's one more force. That applied force that the picture showed, F. To the right, excuse me. Draw it with its tail anchored on the particle, please. Point it in the direction it's acting, so it's pointing to the right. And then label it, F. And now you have your forces. We need to include axes to make it a complete free body diagram. I'm going to choose a plus x axis to the right and a plus y axis vertically up. Doesn't matter where you draw the origin on these axes here, just show the directions. Which way is plus x? Which way is plus y? And my rule of thumb is, if I know the system is accelerating in a particular direction, then I choose one of my axes to be in that direction. I know this system is accelerating to the right. Therefore, I'm going to choose one of my axes to the right. I chose plus x. Okay, the next step in applying Newton's second law is to apply it, to write it down in component form. So we write down the second law by components. That is always how I want you to apply Newton's second law, by its components. Here the important component, i.e. coordinate axis, is x. So when I say write down the second law by components, I mean write this. A sub x equals F net x over the mass of the system. I'm going to remind myself that my system was the two blocks by calling it M total. Okay? I want to see an expression like that written in your work, that you are explicitly starting from Newton's second law for a particular component, in this case x. Now all you have to do next is fill in with symbols what you know about F net x and M total. For F net x, you've got to add up all the x forces. There's only one. There it is right there. The applied force F in the positive x direction. The entire magnitude is in the positive x direction. So for F net x, here's how I write it. Plus magnitude of the applied force. Meaning the entire magnitude of the force is in the plus x direction. And for M total, I just put M1 plus M2. So that's what's in the denominator. Okay? That's my application of Newton's second law for the x direction. Good news is, I know all the numbers for the symbols on the right-hand side, so I just plug in. And I can get a number then for A sub x. The magnitude of the applied force is 3.2 newtons. I'll remind you what the masses were. M1 is 2.3 kilograms, and M2 is 1.2 kilograms. So the total mass of the system is 3.5 kilograms. Notice how I'm writing units. Just go to your calculator. 3.2 is a little less than 3.5. This division is going to be a little less than 1, and I'm going to give 3 sig figs. Technically, I should give 2 since the problem gave 2. but Wiley plus will probably be, have a better chance of being within its 2% if I give 3 sig figs. Now the unit is Newton divided by kilogram, but you should convince yourself that that's equivalent to meter per second squared. That's the common acceleration of the two blocks. They each have that x acceleration. Okay, now we've done part A. We've applied Newton's second law. Okay, I'm going to need more space, and this is not going to let me, oh yeah, there we go. We're going to move on up here, and I'm just going to tell you, I'm going to read to you what part B says, and then we're going to do it. Part B says this: find the magnitude of the force that block 1 exerts on block 2. Remember, the blocks are in contact with each other. Okay, just a quick sketch. They're on the surface, 1 and 2. They are in contact. They're being pushed together to the right by this applied force, so they're definitely in contact with each other. So, block 1 exerts a force on block 2, and here comes Newton's third law, block 2 exerts a force on block 1. We are asked to find the magnitude of the force that block 1 exerts on block 2. Okay. How are we going to do that? Well, we're going to apply Newton's second law. First step, pick a system. Now, I know that you may feel initially here like you're unsure as to what to choose for the system. I don't have a magic answer for you. You learn only from lots of practice what is the wise choice for a system. So when you're still learning this, just go ahead and accept the fact that in working through homework problems, you're probably going to have a number of false starts. You're probably going to say, well, let me try the system to be this, and then try applying Newton's second law and discovering, no, I don't have enough information, it's not helpful. Let me back up and choose something else for the system. That's fine. That's all part of the learning process. Okay? So I don't want to imply that it's going to be always just immediately obvious what you should pick for a system when you apply Newton's second law. There's going to be some trial and error, and that's okay. But here's what I'm going to tell you now. If my goal is to find the force onto that one due to 1, that's what I want, the force onto that comes from 1, I'm going to pick the system to be block 2. You'll see why in a minute when I draw the free body diagram. But my system now is only block 2, not block 1. Okay? My choice. But now that I've made the choice of the system, I have to be consistent with it. So now we draw the free body diagram for this system. Okay? So I'll come over here to the side. There's the surface. Now my dot represents this system, which is just block 2. Just block 2. Let's draw the free body diagram. Again, you should pause the video and try it first for yourself. You'll get more out of this if you do. Okay, did you try to draw the free body diagram for block 2? Well, as I said, the first one that we always draw is gravity, force due to gravity, because that's an easy one. Now that's going to be a short arrow here because block 2 is not very heavy. I'm going to label it FG2, reminding myself it's only F grav for block 2. Did you draw a normal force perpendicular to the surface? In this case, upward. I will label it FN2, the normal force on 2. And I know that those two forces balance each other because there's no vertical acceleration, so the net vertical force must be 0. Now, there's one more force, and it's an important one, and it's horizontal. It's the force on 2 from the push from 1. And it's got to be to the right, yes? Block 1 is pushing block 2 to the right. So draw it with its tail anchored on 2 and pointing to the right. And I'm going to label it like this. It's the force on 2 due to 1. Okay? Remember, there's no friction, so there's nothing else. And if it's part of you wanting to say, wait a minute, there's that applied force F. Remember that one that we talked about in part A? Why didn't I draw it in the free body diagram? Maybe you did when you tried it. But it shouldn't be there. You see why not? Because the system is block 2. Is that applied force being applied to block 2? Directly. Directly. No, only to block 1. In fact, it's the effect of that applied force that's being transmitted to 2 through this contact with 1. It's this one right here that I just drew and labeled F21 that is indirectly coming from the applied force. But the applied force itself is not directly pushing on block 2. And a lot of people struggle with that. When you draw the complete free body diagram for a system, you only draw forces acting directly on that system. This then is the complete free body diagram for block 2. Notice then what is responsible for block 2's acceleration. The 0.914 meters per second squared that we just found in part A of this problem. It's that F21. That's what's giving block 2 its rightward acceleration. Now let me finish off the free body diagram by putting in my x and y axes. Since I know the block's accelerating to the right, I'm going to pick one of my axes to be to the right. I chose x. Plus x to the right, plus y is up. Step 3 is to write down Newton's second law by components. Again, this is how I want you to write it, by components. And the important component here is x. So I want you to write a sub x equals F net x over m2. Right? It's only the mass of 2 here because 2 is the system, block 2. It's really important that you write it that way. A sub x equals F net x over m2. And I look at my free body diagram to get F net x. Well, there's only the one x force, and it's the entire magnitude of F21. So plus magnitude F21 is F net x divided by m2. Now, I already know the acceleration. I found that in part A, right? 0.914 meters per second squared. I know the mass, m2. So just solve for the magnitude of F21. And of course, that's exactly what part B is asking for. So the magnitude of F21 is m2 times a sub x. So that's 1.2 kilograms times 0.914 meters per second squared. I'll give 3 sig figs, 1.10. The unit is kilogram times meter over second squared. That is a Newton. So the magnitude of the force on 2 due to 1 is 1.1 newtons. And it's this force, F21, that is responsible for providing block 2's acceleration. Okay, that's part B. Not hard if you're systematic, right? Be careful. Now let me go on to part C, and I'll read it to you. Part C says, apply Newton's second law to block 1 alone to calculate the acceleration of block 1. Cross-check that with the answer from A, since I found the acceleration of the blocks in part A. This is just a kind of a check to make sure everything's making sense. Okay? All right. So now, first step, pick the system. Okay? It tells me in this part, doesn't it? Block 1 alone. It says, apply Newton's second law to block 1 alone. So, the system is block 1. Step 2, draw a complete free body diagram for the system. So let's do that. Let's do it over here. There's the surface. There's the dot. The dot now represents block 1. Okay? Again, I think you should pause the video and try your hand at it yourself. Draw the free body diagram for block 1. Okay, did you try it? Let's see. Let's put in the easy one first, F grav. F grav 1. Vertically down, a little bit longer than F grav 2 because block 1 has more mass. Did you draw a normal force perpendicular to the surface? In this case, vertically up. I would draw it, and then I would label it Fn1. It's the normal force specifically on block 1. All right, that's the vertical forces, and there is no vertical acceleration, so the net vertical force must be 0, so those two forces must balance each other. That's it for them. We're done with them. Now let's talk about horizontal forces. Forces, I said. More than one. Now, there is the applied force, F, because it is acting directly on block 1. Let's draw it with its tail anchored on the particle and pointing in the direction of the force. The applied force is to the right. So the F, I would draw like that. Please draw the forces with the tail anchored on the particle. You are much more likely to get confused if you draw any other way. Okay? That's the applied force on the block 1. But that's not all. You see where there's one more force? It's not friction, remember. There's no friction. There's a force on block 2 from block, there's a force on block 1 from block 2. 1 and 2 are touching. So there's a force on block 1 from block 2. You see which way that force points? To the left. And I'll label it force on 1 due to 2. And I know that force has to be there because, now let's go back and look at the free body diagram for 2. Let's compare these two free body diagrams. All right, the top drawing is a free body diagram for 2. The lower one is a free body diagram for 1. If there's a force on 2 due to 1, right there to the right, then there must be a force on 1 due to 2 of equal magnitude, but to the left. The forces are on different things, yes? But they do exist. If there's an F21, then there's an F12 of equal magnitude and opposite direction. That means I know what that magnitude is for F12. I know its magnitude is the same as F21, which I just found in part B to be 1.1 newtons. Magnitude. Right? Okay, now, let me get my drawing back up here a little bit higher. Let me put in my choice of axes for this free body diagram. Plus x to the right, plus y up. Okay? You can see them. I think you can tell the y is up. And now, step 3, apply Newton's second law in component form. Here, the most important component is x. A sub x equals F net x over M1, right? The system is block 1. Now you go to the free body diagram to figure out what you put in for the F net x. You have to add up all the x forced components with appropriate plus and minus signs. For example, the applied force, just checked it there in red, its entire magnitude is in the plus x direction. So the first thing I write on the numerator here is plus magnitude of F. But then there's the entire magnitude of F12 to the left, negative x. So the next thing I write here is minus the magnitude of F12. And that's my symbolic expression for F net x. And it all gets divided by M1. And my task is to solve for the acceleration here of block 1. So I know all the numbers on the right, so I just plug in. The magnitude of the applied force, 3.2 newtons, minus the magnitude of F12, which is the same as the magnitude of F21, is 1.1 newtons. And the mass of block 1 is 2.3 kilograms. So you do that math on your calculator, and you get, now I'm going to do 3 sig figs, I get 0.913 meters per second squared. Remember when I solved in part A of the problem, when I applied Newton's second law to a different system, the two blocks together, I got 0.914. Now I applied Newton's second law to a different system, block 1 only, but I still got the acceleration, and 0.913 is good agreement with 0.914. So everything's consistent and makes sense. You see what I'm saying? All right, well, there's one more part. Part D. Get this up a bit, and I will read it to you. Part D says, suppose a force of the same magnitude F, that's the 3.2 newtons, is applied to the smaller block and in the opposite direction. Find the magnitude of the force that block 2 exerts on block 1 and explain why the answers to B and D are different. Okay, so now, just to make sure it's clear, get the big block 1, the little block 2. Now I'm pushing with the applied force that way, to the left, directly on 2. Well, now they're going to accelerate as a blob to the left. They got to have the same acceleration. Magnitude anyways. AX is to the left with magnitude, let's say 0.914 meters per second squared. Right? Because it's still the two blocks, and I'm still pushing with the same size applied force. Now I'm just pushing to the left. So I'm going to get an acceleration to the left, but it's still going to have the same magnitude as when I push to the right, 0.914 meters per second squared. And my task in part D, and the two blocks are pushing against each other as well, is to find the force on 1 due to 2. So now I pick a system, and if I want to find the force on 1, I want to pick for my system block 1. And then I draw a complete free body diagram for block 1. And it's a new free body diagram because the situation has changed. Okay, there's the dot representing just block 1. And now draw the free body diagram. Again, you should pause the video and try it first for yourself. Okay, free body diagram for block 1. We've got F grav downward, so F grav 1. Got the normal force upward, F normal 1. Not the applied force, F. It is acting directly on block 2, not on block 1. The only other force is from 2. 2 is pushing on 1. And in this case, 2 pushes on 1 to the left. So this is the force on 1 due to 2. That's what I have to find. Okay? Let me include my axes. Now, remember my rule of thumb that I use? If I know the system is accelerating in a particular direction, I choose one of my axes along that direction. I know this system is accelerating to the left, so I choose plus x to the left and plus y up. Now that may be a little bit odd to you. You may not be used to that, but you can pick your axes however you want. You just have to be consistent with it. This way, by this choice, the a sub x of the system is positive 0.914 meters per second squared. That's a technical point, but it's important. If you have chosen the plus x axis to the right, then for this block, a sub x would equal negative 0.914 meters per second squared. And if you didn't put that negative sign in, technically it's incorrect. Step 3, write down Newton's second law in component form. So A sub x equals F net x over m1. And there's only a single x force, F12, and its entire magnitude is in the positive x direction. So this is plus the magnitude of the force on 1 due to 2 over m1. I already know what the acceleration is. I already know what m1 is. So I solve for F12 algebraically. F12 equals m1 times a sub x. Notice it's F12 that is responsible for block 1's acceleration. And block 1 has more mass than block 2, doesn't it? M1 is 2.3 kilograms. A sub x is 0.914 meters per second squared. You multiply that out, you get 2.1 newtons. So now the force between the blocks is 2.1. In part B of the problem, the force between the blocks was 1.1. And all I did was switch which way the force was pushing. In the first case, it was pushing against the bigger block. In the second case, it's pushing against the lesser block. And it's interesting that in those two different scenarios, the force that the blocks exert on each other have different magnitudes. In this case, part D, the force between the blocks, F12, is what is resulting in block 1's acceleration. And block 1 has more mass, so I need a bigger force. That's why the F12 is larger in part D than it is in part B. Okay, wasn't mathematically hard problem, but it was really good practicing at applying Newton's laws of motion. And you are certainly encouraged, if you think it would be useful, to watch me going through this example problem on the video as many times as you need to. And we're going to be doing example problems in class of applying Newton's laws. Okay? Because that's how we get good at it, by doing lots of practice. And that's all for this video.